AC systems look confusing, only until you realize you've been relying on them your entire life without ever thinking about it. Welcome to the Learning Studio, where we don't just teach subjects, we strip them down to their intuition so you understand why systems exist the way they do, not just how formulas describe them. Most people think the difference between AC and DC systems is a purely technical distinction taught in electrical engineering classes, but in reality, this difference emerged from very practical needs, long before it became academic theory. DC power is simple and direct. Energy flows in one direction, while AC power constantly changes direction over time, and that single difference shaped how the entire modern world is powered. To see this intuitively, think about everyday electricity use. Your phone, laptop, and batteries all run on DC, which is stable and predictable, making it ideal for electronic circuits. But the electricity that reaches your home from power stations is AC, because sending DC over long distances wastes enormous energy. AC can be stepped up to very high voltages for transmission and stepped down for homes using transformers, something DC cannot do efficiently. Without realizing it, every time you plug in a charger, you're witnessing AC being converted into DC just before your device uses it. At a deeper level, AC systems introduce time-varying behavior, where voltage and current no longer move together. This is where concepts like RMS values explain how AC delivers real, usable power, and phasors help engineers visualize how signals shift in time. In AC circuits, not all power does useful work. Some is stored and returned by capacitors and inductors, leading to the distinction between real power, reactive power, and apparent power, which is essential for understanding efficiency and system design. On a large scale, this is why AC dominates global power systems. Entire national grids rely on AC generation, transmission, and distribution to deliver electricity efficiently, maintain stability, and handle massive loads. Industries, data centers, railways, and cities all depend on careful management of AC power, while DC quietly operates inside electronic devices, renewable energy systems, and electric vehicles after conversion. In real engineering practice, understanding AC versus DC is not optional. It is used when designing power supplies, selecting motors, correcting power factor in industries, analyzing transmission losses, and ensuring electrical safety. These ideas were later formalized and standardized through the work of engineers and scientists during the early power era, allowing electricity to be generated, transmitted, and used at a global scale. Now that the intuition behind AC and DC systems is clear, the next step is to dive deeper into phasor analysis and RMS calculations, where alternating signals stop being confusing waveforms and start becoming predictable, solvable systems. And that's exactly what we'll explore next here at the Learning Studio.